Okay, so the question here is light rail passenger trains that provide transportation within and between cities speed up and slow down with a nearly constant and quite modest acceleration. So a train travels through a congested part of town at 7 meters per second. Once free of this area, it speeds up to 13 meters per second at 8 seconds. At the edge of town, the driver accelerates again with the same acceleration for another 16 seconds to reach a higher cruising speed. So the important thing here to remember is what the train is doing. Sometimes it's under uniform accelerated motion and other times it's under uniform motion. So you got to go through here and kind of decide, okay, what's under uniform motion and what's under uniform accelerated motion. So a train travels through a congested part of town at 7 meters per second. So that means it's under uniform motion. But it's also giving you another bit of detail called the initial velocity. Once free of this area, it speeds up to 13 meters per second in 8 seconds. So if you notice, the initial velocity is given to you right here, 7 meters per second. And it says once free of this area, it speeds up to Okay, so light rail passenger trains that provide transportation within and between cities speed up and slow down with a nearly constant and quite modest acceleration. A train travels through a congested part of town at 7 meters per second. Once free of this area, it speeds up to 13 meters per second in 8 seconds. At the edge of town, the train driver accelerates again with the same acceleration for another 16 seconds to reach a higher cruising speed. So what it's doing is right here, it's giving you, let me see if I can get my highlighter to work. Okay, so right in this point, it's telling you the initial velocity. That's what it's doing. It's saying, hey, it's going through the town at that speed. And then once it's free of that, it accelerates. This is the final velocity. It accelerates to 13 meters per second, and this is your delta t. At the edge of town, the driver again accelerates with the same acceleration. So if it's accelerating with the same acceleration, then you need to find the acceleration that it did through this. And it gives you a delta t of 16 seconds to reach the higher cruising speed. So you have a couple of different questions going on here. You have the first question of really, what is the acceleration? So you need to find your VI, and then of course it's 7 meters per second. You need to find your VF, and that is 13 meters per second. And then your delta t, which is 8.0 seconds. And what you really need to do is you need to find that acceleration because you're going to use the acceleration in the second part of the question. So that's the question. Of course, it's not giving you delta x. So the equation you're going to use is VF equals VI plus AT. You're going to solve this for A. So A is going to equal to, well, let's go ahead and bring it back to the other equation. I skipped ahead a little bit. Okay, again, VF is equal to VI plus AT. So to get A by itself, because you know VF, VI, and T, and you're trying to find A, you need to subtract VI. So that becomes VF minus VI is equal to AT. And then you need to divide through by T. And that G cancels out this. So the formula you are going to be using is acceleration is equal to VF minus VI over T. And of course, your numbers might change over here, but that's the general format to get through that first part. So once you find the acceleration, then it says at the edge of town, the driver again accelerates with the same acceleration for another 16 seconds to reach the higher cruising speed. So guess what you know? Well, you know, he was going, that's where he accelerated to. So in the second part, your initial velocity is going to be 13 meters per second. Your acceleration is going to be the acceleration you found here, and then your delta t is just that 16 seconds. Okay, well, I hope that helped. Okay, so on the second question, we're going to be looking at okay, so on the second question, we're going to be looking at the speed of a skater as she moves from a frictionless part of ice to a patch of rough ice that has more friction, and then back to a frictionless patch of ice. So the very first thing you need to do is you need to outline what you know. Well, a speed skater moving across frictionless ice at 8.8 meters per second hits a 5.4 meter wide patch of ice. She slowly, steadily, then continues on at 5.8 meters per second. So, think about what all this is giving you. This is giving you the initial velocity, VI, is equal to 8.8 meters per second. It's giving you a delta X at 5.4 meters. And then it's giving you a final velocity. How fast is she going afterwards? VF. It's 5.8 meters per second. Now, what's the question over here? It says, what is her acceleration on the rough ice acceleration? So notice what's not given to you. Out of all of these, remember you got to ask yourself, which one of these are not given you? Obviously, we're getting VI, VF, delta X, and A, and the one that's missing is T. So that's the one that's going to dictate which equation you're going to use. So let's go over here and let's look for the one that's not using T. That's using T, that's using T, that's using T, but notice this one's not using T. So you're going to use this equation. VF squared is equal to VI squared plus 2A delta X, and you're going to solve for A. So let's rewrite that up here. VF squared is equal to VI squared plus 2A delta X. So again, how do we get the A by itself? Well, it's just like that equation in the previous problem. You got to subtract VI squared. Don't be scared of the square part. It's going to work out just the same way. So you get VF squared minus VI squared is equal to 2A delta X. And I'm going to stop this because I want you to do the rest of the algebra. I want you to solve this for A. Okay. So if you have any problems, I'll be having a workshop on this today, so just please come up and talk to me. And so we've spent a lot of time talking about graphs lately, and I want to make sure you guys are good at it. But you guys will have to read this graph, and it's not too terribly difficult of a graph to read. So what is the particle's position at time t is equal to 1.0? So you go over here to time t is equal to 1.0, and just remember what I showed you guys on the translating graphs whenever you have a velocity versus time and how to find the position of it. Part B is what is the particle's velocity at time t is equal to 1.0? That's pretty straightforward. That's actually really straightforward, so I'm not going to go into that one. What is the particle's acceleration at time t is equal to 1.0? Again, you know, we talked about this yesterday and the day before, so just be aware of, you know, what does a velocity versus time graph, what all information is given to you. Obviously, you can find position because that's just the area underneath the graph, but you can also know something from the slope. Again, what is the particle's position at 3.0? So this one's a little different because now you have to take into consideration two different parts of the equation. The other one, it was under uniform motion, but this one is under uniform accelerated motion. So there's a couple of ways you can do it. You can look at the area underneath the graph, or you can use the equation delta x is equal to 1/2 VI, the initial velocity of this is 4, plus VF, the final velocity of this is 2, times T, which is 3. What is the particle's velocity at time t is equal to 3? Again, that's pretty straightforward. What is the particle's acceleration at time t is equal to 3? So again, that goes back to understanding what does slope mean. Okay, so let's go on to question 4. So chameleons catch insects with their tongues. Okay, so the trick to this one is, again, realizing that there's two parts. There's a uniform accelerated motion, there's a uniform motion, and also there's a trick in knowing what 20 meters or 20 milliseconds is. So what I'm going to do is I'm going to show you on here, first of all, what 20 milliseconds would convert over to and why. Okay, so 20 milliseconds, let me come over here. 20 milliseconds is the same thing as 20 times 10 to the negative third. But let's even go one step further. Let's convert this back to standard notation. So I'm going to put this down here, 20 times 10 to the negative third. I'm going to put the decimal there, put a couple of zeros out in front, negative third, negative 2, negative 1, and 0. So 20 milliseconds is equal to 0.020 seconds. So that kind of helps, that should help you get through the millisecond issue. Now again, you've got two different things going on here. You have chameleons catch insects with their tongues, which can rapidly extend to great lengths. In a typical strike, a chameleon, the chameleon's tongue accelerates, so it has a time that it accelerates at a remarkable 290 meters per second for 20 milliseconds. Again, what do you already know? There are some things that you can make some assumptions on. What's the initial velocity of the tongue? I don't think final velocity is spoken about in here, but something is, you know the time is equal to 0.020 seconds, and you know the acceleration is equal to 290 meters per second squared. And then there's a second part here. It's going to move on at constant velocity. So we're not going to deal with the constant velocity just yet. Whenever you have a uniform motion with a uniform accelerated motion, in other words, you have one part that is accelerating and then you have something going on afterwards where it's going to stay the same speed. You can't work those together. You've got to separate them out. So the question that it's asking is, during this total time of 50 milliseconds, again, that's the 20 milliseconds plus 30 milliseconds, how far does the tongue reach? Well, the 30 milliseconds is pretty easy. That's just velocity is equal to distance over time. Distance is equal to velocity times time. You just got to know the velocity and the time. You know the time, that's 30 milliseconds. The velocity, however, I don't believe is given to you, so you'll have to also work out that final velocity in this problem as well. So we really have a couple of questions. We need to know the final velocity, and then we need to know delta x. So let's figure out delta x first. Again, our VI, we do know it. The tongue was still sitting still, so initial velocity is 0. So to find delta x, you're going to come back to this equation, delta x, because we don't know anything about VF yet. VIT plus 1/2 AT squared. So again, the initial velocity is 0, so that gets to go to 0. So you get this formula, delta x equals 1/2 AT squared, and you solve for delta x. And at that point, there's a lot of equations that can find VF. For instance, VF is equal to VI plus AT. That would do it. So once you know VF and you know delta x, the question is how far does the tongue reach? Well, you know VF, so you can plug that in right here, because the final velocity of that tongue coming out here is going to be the same as whenever the tongue is going through the uniform motion part. So you're going to use this final velocity for the velocity during this part, and during the part that the tongue's coming out, it's just velocity is equal to distance over time. And again, I covered it up here, so distance is equal to velocity times time. Okay, that should help you out with that one. That's an interesting question. Okay, so you're driving down the highway late one night at 19 meters per second. Look at that, you already have some information, 19 meters per second. When a deer steps into the road 44 meters in front of you, your reaction time before stepping on the brakes is 0.5 seconds, and the maximum acceleration of the car is 11 meters per second. So it's giving you a whole lot of information. Let's go ahead and write that down. It's giving you initial velocity is 19 meters per second, It's giving you a delta x of 44 meters. It's giving you a delta t of 0.50 seconds, and it's giving you acceleration of 11 meters per second. In fact, the only thing it's not giving you is VF, so that should give you some ideas of which equation to use. So how much distance is between you and the deer when you come to a stop? So how much distance is between you and the deer? Well, now, notice the question is when you come to a stop. So you have to find, well, how much distance does it require me to stop? So really, did it give you the delta x of how much distance is requiring you to stop, or is it giving you the delta x between you and the deer? Okay, so this is interesting because it's giving you the delta x between you and the deer, not how far it takes you to stop. So you have to find delta x. So you have to go in there and you have to realize, okay, this is, I know initial velocity, I know delta t, I know a, I don't know anything about vf. This is the same formula as you used a while ago. Delta x is equal to vit plus 1/2 at squared. And again, this one, though, is interesting because you actually have an initial velocity. So you have to go ahead and use that. And you know the acceleration, you know the time. It's just a matter of putting in the number. So what is the maximum speed you could have and still not hit the deer? So this one's doing it backwards. Now, you don't know the initial velocity. What should your final velocity be, though, for this one? Where you want to be able to stop before you hit the deer. So in this question, you need to have a VF equal to 0. The delta x, well, you don't want to hit the deer, so you need to stop within 44 meters. The VI, that's the part you don't know, right? And the acceleration due to gravity is 11 meters per second squared. I'm sorry, that's not due to gravity. That's just acceleration. We've been talking about gravity too much. Now this one, though, we don't know what the time is. We don't know what the time is. So we got to choose an equation that does not involve time. So for this equation, I would probably do, so again, we got to choose an equation that does not involve time, and all of these three involve time. It's that one right there, VF squared equals VI squared plus 2A delta X. So I'm going to go back over to the problem. I'm going to write that down. VF squared equals VI squared plus 2A delta X. I'm going to put that in parentheses. So again, all you're doing now is solving this for the initial velocity, which I'm going to let you do that part because I think you're probably capable of doing it now. Okay, so that gets you through question, I believe that's 4. Okay, so I was wrong. It's question 5. So now we're on to question 6. One simple model for a person running the 100-meter dash is to assume the sprinter runs with constant acceleration until reaching top speed, then maintains that speed through the finish line. If the sprinter reaches his top speed of 11.5 meters per second in 2.74 seconds, what will be his total time? So again, you're going to have a part that's accelerated motion. You're going to go in there for the accelerated motion. That's during the accelerated time right here, right? And you're going to find how long it takes, and then you're going to find the time that it takes for him to run it past the accelerated motion. Okay, so and in addition, you got to remember the initial velocity is 0 and the final velocity is at 11.5 meters per second. So you know the initial velocity, you know the final velocity, you know the time. You really only need to find the delta x. Once you find the delta x of the acceleration, then you could subtract it from 100, and then using his final speed, his top speed, and that new distance, you can find out how long he was under uniform motion, and then add the 2 times. Okay, so this one's not nearly as tricky, but because it's in the y direction, I wanted to give you guys some heads up on it. It says an excellent human jumper can leap straight up to a height of 90 centimeters off the ground. That's almost a full meter, which is pretty astounding, actually. So what you got to ask yourself is this. You know delta x is equal to 90 centimeters. You know acceleration due to gravity is equal to negative 9.81 meters per second squared. What else can you coax out of this problem? Well, I'm going to ask you at the very top, the initial velocity, the final velocity is equal to 0. So how does that help you? Well, you know final velocity is equal to 0 down here. To reach this height, with what speed would the person need to leave the ground? It is asking for initial velocity. So really the only one that's not given to you is t. So you're going to use that same equation, Vf squared is equal to Vi squared plus 2a delta x, and solve it again for Vi squared.